So in this video, we're going to be talking about properties of compounds within homologous series. We're going to start off first by talking about intermolecular attractions because those are going to help to determine properties such as boiling point as well as solubility. Okay, so as a reminder of what intermolecular attractions, which are also known as intermolecular forces, are, they are types of attractions that happen between molecules. Okay, so all of these attractions that we're going to talk about are weak, but like I said, they affect properties such as boiling point and solubility. So the first one is London forces, which are also called London dispersion forces. Okay, and those are going to be present within all compounds. Now, the reason why all compounds have this is because London forces come from the attraction between a positive nucleus of one molecule and it's attracted to the negative electrons of a nearby molecule. Okay, so essentially, the larger the molecule you have, the more electrons and protons are going to be present. Therefore, the larger molecules are going to experience a greater degree of London forces than smaller molecules. Okay. Now, another way you can determine which molecule has a larger London force, you can also just think of it as the bigger the molar mass, the bigger the London force. Okay, so London forces, those affect boiling points. And like I said, all molecules have these forces. Okay, so if we were to draw out what a London force looks like, this is what it'd be. So we've got our positive nucleus. The reason why we're calling the nucleus positive is because that's where the protons are housed. Okay, and then we have the electrons for that molecule. Now for a nearby molecule, and let's say it's of the same substance, we have same situation happening. So what London forces are the attraction between the protons in the nucleus of one molecule and the electrons of a neighboring molecule. Okay, so these are London forces. Okay. Moving on to dipole-dipole attraction. So these are only going to occur in polar molecules. A dipole-dipole attraction is when the negative end of a polar molecule is attracted to the positive end of a polar molecule. So you should know that definition. Okay, now this form of attraction is generally weaker than London forces, but it's going to be important for determining solubility. Okay, the reason why it's important for determining solubility all comes down to this rule of like dissolves like. So polar molecules are going to dissolve other polar molecules. Non-polar molecules are going to dissolve other non-polar molecules. However, you can't mix and match. A non-polar molecule is not going to dissolve a polar molecule. Okay. So if you have a high degree of polarity in your molecule, you're going to have a high dipole-dipole force. Okay, so the bigger the polarity, the more dipole force compound is going to experience. So if we had to draw this out, what it would look like is we have one molecule here, there's the positive end of it, the negative end of it, and then we have another molecule over here, which could even have the same identity. So like these could be the same substance, just different molecules of the same substance. Okay, and the attraction just happens between the positive end of one molecule with the negative end of another molecule. Okay, so the reason why one side of both of these molecules is more negatively charged, it has to do with electronegative atoms in the compound. So if one side of your compound has more electronegative atoms in it, it's going to essentially pull the electrons in the bonds. So by it, I mean the electronegative atom. Because of its electronegativity, it will basically attract the electrons in the bond towards itself, and that is what causes one side of the compound to be slightly more negatively charged than the other, is just because the electrons in the bonds are skewed to one side, essentially. Okay, so if you're wondering about the definition of, okay, what is electronegative? Okay, all that means is, or all the word electronegative or electronegativity captures, is just the ability of an atom to draw electrons to itself. So again, how you determine whether an atom is highly electronegative or not is you're going to take a look at your periodic table, and for this version of the periodic table, the electronegativity values are just above the symbols for each element there. So as we can see, fluorine is more electronegative than carbon, which means fluorine has a greater ability to draw electrons in bonds connected to fluorine towards the fluorine atom, okay, compared to carbon. Okay, so based off of the electronegativity scale that this periodic table uses, 4 is your maximum number. Okay. Now, if you were wondering about, okay, what is a polar molecule, we'll get into a few more details about what is polar versus nonpolar just in a little bit here. Okay, but make sure you also highlight this. The bigger the polarity, the bigger the dipole-dipole force. Okay, the last intermolecular force, that's going to be hydrogen bonding. So you only have hydrogen bonding in a polar molecule. So let's write that in. Okay, so there's 2 requirements for hydrogen bonding. It only is going to occur in a polar molecule, and hydrogen must be directly attached to either a fluorine, nitrogen, or oxygen. Okay, so hydrogen bonds are going to be stronger than regular dipole-dipole attractions, okay, and they are going to affect things like solubility as well as boiling point. Okay, so getting to polar versus nonpolar, how do we decide if a compound is polar or nonpolar? There's a couple of different ways. Okay, so looking at the diagram here, okay, we have two hydrogens, and these two dots in the center, they're just the electrons that are shared between these two hydrogens. So in other words, these two electrons here represent a bond between these two hydrogen atoms. Okay, now as you notice, like these values are the electronegativity values and they are the same. What that means is that each of these hydrogens, so I'm just drawing in dipole arrows here, each of these hydrogens are pulling on these electrons with equal and opposite forces. Okay? Which essentially what that's going to do, because each hydrogen atom is pulling with equal and opposite force, they essentially just cancel out. Which means that this is a nonpolar molecule. Okay? So let's just write out some of the stuff I said. So these numbers describe electronegativity, which is the ability of an atom to pull electrons towards itself in a bond. Okay, so they go from 0 to 4. And then with what I said about the hydrogen, if the atoms pull on electrons with equal and opposite force, they cancel out. Okay. So if they cancel out, then that means the compound is going to be nonpolar. Okay, so polarity just tells you if the sharing of electrons is equal or unequal. Okay, so if atoms pull in equal and opposite directions, okay, then they cancel each other out, the electrons are shared equally, and the molecule is nonpolar. Okay, so we would call this a nonpolar covalent bond. Covalent just means that the bond is happening between two nonmetallic elements. Okay? For unequal sharing, let's just look at this picture right here. So hydrogen has an electronegativity value of 2.1, fluorine has a value of 4. Okay? So if we were to draw a dipole arrow, it would go towards fluorine, so the arrow always points in the direction of the more electronegative element. And as you can see, the electrons are skewed more towards the side of fluorine. So these electrons here are representing the bond between this hydrogen atom and this fluorine atom. And because fluorine is more electronegative, the electrons within the bond are skewed a bit more towards the side that fluorine is on because fluorine is more electronegative. Okay, so This would result in unequal sharing of electrons. I should be adding that in. So this shorthand just means electrons. And I should add that in over here too. So if your electrons are unequally shared, you have a polar covalent bond. Okay, and again, covalent just means you have a bond between two nonmetals or two nonmetallic elements. Okay, so I know I've mentioned the definition of electronegativity. Let's just write that out while we have space here. Okay, so electronegativity describes how strongly an element can pull electrons towards itself. All right, so now that we've covered some background of intermolecular forces, now we can get into homologous series and how these intermolecular forces affect properties of homologous series. So what is a homologous series? It's when you have a series of organic compounds with similar general formulas. So you should know what a homologous series is. Okay. So members of a homologous series have similar chemical properties due to the presence of similar or the same functional group. There is a gradation in physical properties as a result of the increase in molecular size and mass. For example, ethane has a higher boiling point than methane. So ethane is just an alkane, so there's only single carbon-to-carbon bonds, and it has 2 carbons in it, whereas methane only has 1 carbon in it. So ethane has a higher boiling point than methane since it has more van der Waals forces, which is just another name for intermolecular forces, with neighboring molecules. And the reason why this happens is because ethane has an increased number of atoms making up the molecule compared to methane. It has 1 more carbon and a few more hydrogens attached to it. Okay. So organic compounds in the same homologous series, they're typically going to vary by a CH2. And essentially every category of organic compounds could be considered a homologous series. So alkanes, if you're considering methane, ethane, propane, butane, pentane, that's a homologous series right there. Okay? Same with alkenes. If you're thinking of ethene, propene, butene, pentene, that's another homologous series. Okay, so here's some more examples. The first one is just with alkanes, methane, ethane, propane, butane. And the next one underneath it talks about what a homologous series with alcohol groups in it would be. So hexanol, decanol, ethanol, butanol, those are all part of this same homologous series because they all have the functional group of a hydroxyl or an OH, which is what makes them an alcohol. Okay, so here's some more examples of some homologous series. Okay, so I mentioned alkenes. So if you're looking at the line diagrams for that, so this would be ethene, propene, butene, one, two, three, four, five. Okay, and then pentene. Okay, so all of these have a double bond in them, and we're just adding on one more carbon as we go through this homologous series. Okay, well, we're adding on one more carbon plus the implied hydrogens that make it so that each carbon has 4 bonds in it. Okay, so as we go up in size of the compound, essentially what that means is we're going to have more London forces. Okay, and as we just covered, London forces, those affect boiling points quite a bit. So essentially what would happen here is we could say that this compound here, because it has more London forces, we would expect it to have a higher boiling point than ethene over here. So I'm just going to abbreviate boiling point to BP, lower boiling point. Okay, if you wanted to do a homologous series with organic halides, it could look something like this. Okay, so so again, as we go through this homologous series of organic halides, we would expect to have a higher boiling point with this compound compared to this compound, because the one on the right has more London forces compared to the furthest most left one over here. Okay, one last one that I wanted to talk about here would be with alkynes, so compounds that have triple bonds in them. So this would be ethyne, propyne, and butyne. Okay, so some things that kind of trip up students is that there's kind of alternative ways to draw some of these compounds here. So, and it's a little bit confusing for students to essentially count up their carbons. Okay, so with this drawing that I've done above, okay, we have carbons here, here, and here. Okay, but with this drawing, sometimes it's harder for students to see how many carbons there are. These two compounds are the same compound, they're just drawn a little bit differently. Okay, but we still have this carbon is this one in this different drawing. This carbon would be right here, and then this carbon would be right there. Okay, same for this other diagram. So these are the same carbon, these are the same carbon, these are the same carbon, and these are the same carbon. So oftentimes what I'm just trying to say here is students have a bit harder time when triple bonds are involved and like the line just kind of keeps on going straight. It's a little bit more difficult. Okay, so I'm just going to draw another way of doing this type of compound that kind of makes it a little bit more clear. So this still has 4 carbons in it, and where the carbons are, right there, 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 and there. Okay, so all of these compounds are the same, it's just different ways of showing the same compound. Okay, and how you draw your compounds can make it a little bit more difficult to figure out where your carbons are.